Hello everyone. I decided I was going to make a video lecture for cross products as opposed to using the text. I feel the text does not do justice to cross products that they deserve. So I'll give you guys a short lecture on cross products that you can use for this week's or this unit's assessment. So let's start with what in the world is a cross product. Let's say I have two vectors sitting in real space R3. Okay, so we need to keep that in mind. We're working in R3 space here. I need to get used to this technology thing while I'm doing this. Anyway, so we're in R3, and we have two vectors sitting there. Okay, so let me attempt to draw two different vectors here. We'll call that vector A. We'll call this vector B. So, what in the world is the cross product? The cross product is a third vector that I'll draw like this. Okay, this is A, vector A cross with the vector B. Okay, now what's special about the cross product is that it is orthogonal or perpendicular to both original vectors. So it's orthogonal to A and it's orthogonal to B at the same time. Okay. Now, we'll get into why that's so great a little later, but let's talk about some of the properties of the cross product. First off, a very interesting equation. If I take the magnitude of the cross product, A cross B, this is equal to the magnitude of A, the vector A, times the magnitude of the vector B. Remember, each of these are scalars, so this product makes sense. This is the normal product, and we're going to multiply that by sine of theta, theta being the angle between A and B. So if we look here, this angle here is theta. Okay, so I can figure out the magnitude of this vector. I know it's orthogonal to both A and B. We have one last question. The way I've drawn this, I have the vector facing up, but we have another potential vector. So if I redraw A and B here, carefully. So here we have vector A, here we have vector B. I could have drawn, well, that won't really quite work, but the same vector only in the exact opposite direction. So this would be potentially A cross B here. Okay, so we know how long the vector is, and we know the idea of the direction, or the line that the vector is sitting on, this kind of up-down line, if you will. But in terms of uniqueness, is it up or is it down for the vector? Let me write this B here. Vector B. And in order to figure that out, we need to use the right-hand rule. So I'm going to attempt to draw this. My drawing skills aren't great, and I'm using this digital pad thing, so this will probably be a complete failure. But if I have my vector A, my vector B, that's A, this is B down here. Now, if I draw a hand coming out this way, and then I wrap my fingers around. Okay, so my finger gets wrapped around that way. This is now, it has to be my right hand. So this is my palm sticking out this way towards the direction of A. I feel like my drawing ability is going to be a big hindrance to understanding here, but we'll see. Okay, so take your right hand and just kind of look at your right hand now. And you'll see that if you wrap it from A to B, your fingers, your thumb sticks up, and that is the direction of the cross product. This is known as the right-hand rule, A cross B here. Oop, my computer needs to catch up with itself. So you first off point your hand in the direction of the first element, the A, and then wrap your fingers to the second vector B, and the direction your thumb is facing is the direction of this vector. Okay, so we have here, this is a unique vector. This is the one that actually would apply. This one here, and this tablet takes getting used to. This one is actually the negative of the cross product. Okay, so we know the direction. We know it's orthogonal or perpendicular to both vectors A and vector B, and we know the magnitude based on this formula. Right? We can figure out the magnitudes of A and B. We can figure out the angle in between them. So we can figure out what this vector is, and it is the cross product. I kind of wanted to start with a little bit of a geometric idea behind what we're looking at, so this doesn't seem like it's crazy out of the blue stuff that we're doing. Now, how do we, in practice, calculate what the cross product is? Well, here, let me make a new page here. Where did my mouse go? Oh, did this thing die? I think it might have died. Page. Nope, we're still in business. Maybe. Oh, back and forth here. Shoot. Okay, well, we'll give it a shot. So let's say I have a vector A. Just go back to my mouse, so this will look even worse. Let's say I have some vector A, and I think it's best to really look at this through example. So I'm going to say my vector A is the vector 0, 1, 1. I'm pulling this example out of, this is 1A in your text. Vector B is equal to 3, negative 1, 2. All right. Now, your text has a very convoluted and uninformative way for calculating what the cross product is. I'm going to give you a slightly different way. Let's say we take a 3 by 3 matrix. In the middle row of this matrix, I'm going to put in the A component. So this matrix is going to represent A cross B. Okay, so the middle row is going to be the A. Middle row is 0, 1, 1. Bottom row is B. It's very important that the order be put in correctly. So if it's A cross B, A goes in the middle row, B goes in the last row. Now in this top row, I'm going to put in my orthonormal basis, the standard normal basis for R3. Your book uses E1, E2, E3. I'm going to use IJK because I'm a lot more used to that, and I know at some point I'm going to write IJK, and someone's going to look at me like I'm crazy, so I might as well introduce it in this manner. Okay? IJ and K are just standard normal vectors. We'll get into what they are in just a bit. So, I have a 3 by 3 matrix. My cross product should be a vector. Right? Let's go back and look at our picture here. We have A, we have B. Our cross product should be a vector. So we need to get a vector out of this. Okay? Well, let's take the determinant of this matrix. If you don't know what determinants are, or how to calculate a determinant, I'll provide another video for you. Just let me know. So, taking the determinant of this matrix, we get... I'm going to go across the top row here. I'm going to have I times the minor 1, 1, negative 1, 2, the determinant of that minor, minus J, let's not forget the minus, that's important, times the minor determinant 0, 1, 3, 2, and lastly plus the vector K times the minor 0, 1, 3, negative 1. And if we calculate this out, we get, let's see what here, 2 minus negative 1, so that's 3I. We have 0 minus 3, but the minus 1 up there, so it'll be plus 3J. And here we have 0 minus 3. So, my computer needs to catch up with itself again. But it'll be a minus 3K. Minus 3K. Here we go. So, what in the heck does that mean? Well, this is a vector. It's just in non-standard notation. I believe what you are more used to would be something along the lines of 3, 3, negative 3. The I, j, and k represent the first, second, and third components. Another way of thinking about it is that I is the vector 1, 0, 0. J, this is sloppy, is the vector 0, 1, 0. And k is the vector 0, 0, 1. Okay, so if we look back at this equation here, what we're saying is 3 times the 1 in the first component, okay, that gives us our 3 here. 3 times the 1 in the second component, that gives us 3 here. And negative 3 times the 1 in the third component gives us the negative 3 here. All right, so this is just kind of a different way of looking at vectors in terms of I, j, and k. And it is extremely useful when calculating cross products. Okay? So let's do another example. Let's see, new page. Why don't I calculate? I will do 1b from your text. So 1b from your text, we have the vector u. U is given as the vector 3, negative 1, 2. And the vector v is given as 0, 1, 1. Okay? Now, I want to calculate u cross v. U cross v. So I need to set up my 3 by 3 matrix. First row is ijk. Yeah, this is hard to do on a mouse. For u, we have 3, negative 1, 2. And for v, I have 0, 1, 1. Okay. So what do we get here? I'm going to do this determinant in my head a lot faster and not really write out the steps. Feel free to follow along on your own if you want to calculate the steps. What are we going to get here? Negative 1 minus 2 is negative 3 for the I component. The j component, remember the negative in front, so this will also be negative 3. And the k component is simply 3. Okay, so that's how we're going to calculate cross products, is using 3 by 3 determinants with I, j, k in the top row. Now, interesting question. Why do we care? What is the point of cross products? Like I explained in the beginning, let me go back a few pages here. We have that the cross product of two vectors gives us a third vector that is orthogonal or perpendicular. Let me write that down. Orthogonal. This is really hard to do. That's the same as perpendicular. Perpendicular. I hope I'm spelling that right. Orthogonal is more of a mathematician, I'm a smarty pants way of saying perpendicular. So feel free to start peppering that into your normal conversation. So why in the world do we care about finding a orthogonal vector to two vectors? Well, one thing is this handy-dandy formula for finding the magnitude. It is very easy to find the magnitude of vectors and fairly easy to find the magnitude of a cross product. So if I give you two vectors A, B, you can calculate the cross product and find the magnitude of all of those. And this is another way of calculating the angle between two vectors. Finding the angle between two vectors isn't necessarily easy. Now, of course, we also have another formula for calculating the angle between two vectors given by the dot product. So if you're not recalling that, go back to the dot product section and review that, because that's very important, obviously. But when do we need a vector orthogonal to something? That is useful in some situations as finding the equation of a plane. In order to define a plane, what we need is my computer to catch up with itself. Well, more specifically, we need things like a point on the plane. Oop, why is this not responding? Ah, my computer's going nuts. Here, let me just make a new page. So let me draw a plane. Oh my gosh, why is this pen just constantly writing? Turn off. Stop. Stop, pen. Stop. Oh, I hate this thing. Okay, let me try this again. New page. Okay, plane. Like I was saying, what we need in order to define a plane is a point on the plane, call that P, and a normal vector. This is section 1.3. Okay, we'll call our normal vector N. Okay, so what we can do, oftentimes we're given problems where we know a little bit about the plane and we want to find the equation of a plane, but for instance, we're not given like a normal vector. Maybe I'm given a point on the plane and two vectors on the plane, or two vectors parallel to the plane. Okay, well, I can take the cross product of those two vectors and I'm going to find the normal vector to the plane. And so it's a really easy way to find the equation of a plane. Let's look at 4a from your text. 4a is wanting the equation of a plane passing through the point P, where P is 1, 0, -2, and parallel to two vectors. The two vectors we want to be parallel to, vector u, which is given by 0, 1, 1, and vector v, given by 3, -1, 2. Okay, so like I said, in order to find the equation of a plane, we need a point of the plane, which we have, and we need a normal vector. Our normal vector is simply the cross product u cross v. Okay, so let's calculate what that cross product is going to be. Set up our 3x3 matrix, I, J, K. The u vector is 0, 1, 1. The v vector 3, -1, 2. That was a little messed up. Okay, so what do we get here? Once again, I'm going to do this really fast. Feel free to do this on your own if you want to check my work. I am possibly wrong. Like I said, I'm doing this all in my head, just really fast. 3, 3, -3 is our normal vector here, it looks like. So, in the end, I want to find the equation of this plane. I use my normal vector as my coefficients for x, y, and z, so I get 3x plus 3y minus 3z, and I need to be equal to some constant. In order to figure out what that constant is, I'm going to plug in my point as the values x, y, and z, because I know the point satisfies this equation. So if I plug in that point for the values, I get 3 times 1 plus 3 times 0 minus 3 times -2. And what do we get here? That's a 6. It looks like a 9. So the equation for our plane in the end here is 3x plus 3y minus 3z equals 9. I can simplify that a bit if I want. I'm a little, attentive, so why not? X plus y minus z equals 3. Just divide the whole thing by 3. Isn't that pretty? Oh, it's such a beautiful plane. So, yeah, cross products are really great for finding equations of planes. For your reading assessment, I have you doing a few problems related to this. One of which is just computing a cross product, similar to what we did. I gotta go through all my junk here. Here and here. Another equation has to do with finding the equation of a plane, similar to this. So go through those, try those practice problems. There are other practice problems in the text that you're more than welcome to approach. If you feel that after all of that, you still are a little lost on how the whole cross product idea works, let me know, send me an email or something, and I'll try and come up with more problems for you and we can work out some more stuff. So I hope this was informative for you. My first time trying this little recording thing, so hopefully this works. I'll see you guys in class whenever the next session is. All right, goodbye.